Well, my solar energy system has been operational now for 2.5 years, so I have some good performance data to share. I have a series of slides that I will go through to detail how I made the system. It's a solar panel array of 4 rows with each row 10 panels long, so a total of 40 panels. Each panel is about 2 meters by 1 meters, which is a standard size, and generates over 40 volts and 9 amps per panel. So the total system generates over 400 volts at 36 plus amps for just over 14 kilowatts. I'll show a few graphs at the end so you can see how it has been performing. The array is set up to face south with variability of the tilt axis. I live at approximately the 44th degree latitude, so it can be set up at one angle and left there, which is about 45 degrees. But instead I use 2 angles, a summer angle at 20 degrees and a winter angle at 58 degrees. Adjusting twice a year improves the effectiveness from 71% to 75%, so plus 4%, with 100% being full sun following. With this adjustment, I calculate an additional savings of about $120. So for a 30-minute job for me and my wife, twice a year, that's not a bad return on an hour's worth of our work. You're probably thinking, wow, that's a lot of electricity. Well, I actually heat my house with a do-it-yourself heat pump system, and I'll explain that on a future video. I also have a heated tile floor, an electric hot water heater, and an electric oven. So I'm essentially net zero for my annual electric usage. This picture here is of my solar array from last spring after it was set to a 20-degree summer position. Here's a similar picture, but now in the winter position of 58 degrees. The angle change in the winter not only improves the solar collection, but the increased angle helps with snow removal. So, how did I build the array? Well, it's a mix of treated lumber and purchased mounting hardware. I use 6 treated 10-foot long 4x6 posts for each row, so a total of 24 posts. At our latitude, the frost can be usually up to 42 inches, so this gave me about 6 feet above ground. Each post sets on a concrete pad created with a bag of cement mix and a second bag poured around the post. After the cement mix powder solidified, I used a transit to mark a common level on each of the posts for hardware attachment and cut them to length. I then made the mounting and diagonal braces with treated 2x4 lumber. I then used iron ridge hardware to transition from the treated lumber structure to the solar panels. A very simple design that has held up actually quite well. To change the angle position between the summer and winter, all we do is just remove all 6 3/8-inch lag screws at the bottom of the diagonal brace, move the tilt angle, and then reinsert the lags at the new position. By the way, I also have a position set at 0 degrees. This was used for initial panel install and made installation work very, very easy. Each panel was tested before connecting. I used 2 lengths of 10-gauge wire to connect each row to the inverter located in the barn over 100 feet away. The inverter is mounted inside. The inverter makes quite a bit of noise, mostly due to the cooling fans, so if you're doing a similar project, be conscious of the noise level. The inverter is a Fronius Primo 15 kilowatt unit. My system is only 14 kilowatts, but the next smaller unit was too small. I can run this unit higher if I ever wanted to add an additional row of panels. I ran 4 lines of 6-gauge wire and a conduit over to the exit side of the barn, where I installed a fused disconnect on the outside of the building. From there, I connected directly into the panel supplying power to my house and barn. Consumers Energy has a process called net metering, where they take my excess energy generated and give me credit at the same rate at which they charge me for usage. So, think of them as being my seasonal battery. I generate excess energy in the summer months, for which I get credit. I then draw it back in the winter months when my energy use is much higher due to heating with a heat pump at the same rate. So how has the system performed? This is a bar graph of 2021 by month showing kilowatt hours for a total of 18.17 megawatt hours. By the way, March was an exceptionally good solar month, so generally I would expect it to follow a somewhat normal distribution. As an example, this graph is the month of April. As you can see, there is quite a significant amount of energy variation day to day. It just depends on the amount of sunshine. We normally would change the angle around April 1st. We didn't change until the 12th. You can see from the graph we could have actually generated a little bit more energy if we had changed a week or so earlier. This is a plot of power in kilowatts for the date of April 30th. I chose this day as it was the highest solar day of the entire year. The sun angle is important, of course, but also the length of daylight hours, the sun intensity, i.e. no clouds or also low humidity. May and June also had some very high days, but this was the highest of the year. Unfortunately, net metering is no longer available from Consumers Energy. Effective last year, it was changed to what they call Distributed Generation Program. I don't know the specifics, but I believe the amount of credit has been reduced. Fortunately, my system is grandfathered for 10 years. My system cost $16,000 with me and my wife doing most of the work. There was a 30% federal government tax savings, which brought down the total cost to just over $11,000. Given the electrical savings of 18.17 megawatt hours, the payback is under 4 years.